think we have everybody. Well, welcome all. My name is Meredith Portsmore. I am the director of Tufts Center for Engineering Education and Outreach. And we do a lot of exciting things at the center in integrating engineering from kindergarten through college in all kinds of exciting ways. And I'm really excited today to have an amazing presenter here who has a background in engineering, music, acoustics, and more that's really been thinking about music and music engineering and all the ways that music and engineering connect, both as a way to excite students about possible STEM pathways, as well as the other way to think about how engineering impacts the way musicians play and interact with their discipline. So, Kelsey, I'm going to hand it over to you to share with our great audience today all of your information and resources.
Great. Thank you so much for having me. So, like Meredith said, my name is Kelsey Rogers. I am the co-director, one of the co-directors of the music engineering program at Tufts. I have a background in acoustics, actually worked as an acoustics consultant, so I would get hired by architects to help them design buildings. And I've been teaching classes at Tufts for several years. So yeah, background in engineering, music, acoustics, and very excited to talk with you today about how you might bring this into your own classroom. Um, so give me just a moment to share this. Okay, I think we should be good there. All right, great.
Do
So
you see
thanks.
your the bar from the web browser? I don't know if there's a way to do full screen share.
Let's see. I think that might be the best option so that I can also see my own notes. Is
All right,
that
we'll go with it then.
we'll go
That's
with it?
great.
Okay. Um, all right. So we're going to talk about a couple of different things today. Music engineering is, the words music, engineering, how they fit together is kind of an ambiguous phrase. So it, may mean one particular thing to you. It may mean nothing. It may mean a lot of things. So I'm going to kind of demystify what that means in the context of Tufts and what we do in music engineering and how we think about it. I'm going to give a demonstration of how you might approach teaching about the physics of sound and musical instruments through a brief demonstration, and then walk through an activity that I, would suggest offer that you might bring and adapt in your own classroom as a vehicle for bringing music and engineering together for students of a variety of ages, variety of backgrounds. This can really be scaled up or down a number of ways. So let's start with, what are we talking about? What is music engineering? So when we think about this in the kind of Tufts context, we're really thinking about any and all intersections between music and engineering. One of the things that people often think of first is something like a recording engineer or a sound engineer who is, recording audio, producing audio, those kinds of things, which we definitely have at Tufts. We have recording and production courses. And that's, also that's, a great area to attract students of different ages into this realm. But it's actually one of several other possible intersections too. So we're also thinking about the design and construction of instruments, including traditional acoustic instruments, traditional and non-traditional acoustic instruments, anything that, you make that can make some sound. Also electronic instruments. Room acoustics design. So again, my background is in architectural acoustics and room acoustics, thinking about the way that sound moves in a space and how we can design a space to sound really good. Um, Design of loudspeakers, headphones, microphones, other kinds of consumer electronics, even the design of consumer products like hair dryers and blenders and things like that, or drones that make noise that you want to control in some way. That's a whole area of acoustics and noise control research and careers. So there are lots of possible intersections for students who are interested in engineering to have music and sound be a part of that, or students with a music background to have, to kind of see it through the lens of engineering and use and, learn how to use use engineering skills to see their music, to see sound in a different way. So we're going to focus in on acoustic musical instruments with the activity in just a moment. But in general, we found this to appeal to a really wide range of students. I've mentioned that this can work well and kind of scale up and down for a variety of ages. Um, and this really is something that we've designed both through the courses at Tufts and also through working with high school and younger students. That this is something that activities like this can work for students who have a STEM background, who maybe are already interested in engineering and engaged in those classes and want to learn about another kind of specific application in the world or intersection, whether or not they have a music background. This is, another way to practice engineering or to learn something about engineering. And it's also great for students who are interested in music, whether or not they have a STEM background. The kinds of activities that I'm going to talk about and the one that we'll walk through today, that, there's no like prerequisites or things required to be able to do these things. And if there's a student who's interested in music, this is a way for them to see their instrument, see their music, and understand it in a different way. And it helps to broaden the way that students think about the world. It also can help them to kind of, think about what it means to combine what they might be thinking of as their kind of academic interests and what may feel like extracurricular interests, and think about how those can come together. My own story is one of trying to bring music and engineering together. Which for me were very kind of extracurricular and academic interests. But I find that kind of theme resonates well with students who are starting to think about what they might study in college, or what internships they might look for, or career paths down the road, to think about kind of expanding their horizons to how they might be able to combine, an extracurricular passion or something along those lines with what they're studying in school, and kind of widen their horizons. Um, so the music engineering program at Tufts has actually existed for almost 30 years. It's an undergraduate minor program, so there are a bunch of different classes offered to Tufts students. Classes that are offered through the mechanical engineering program, other departments, other engineering departments, as well as lots of classes through the music department. So it's a very interdisciplinary minor. Lots of Tufts students take these classes who don't necessarily complete the minor, but are looking for something that, gives them a new application of engineering that they hadn't known about before, or gives them a class that feels really different from the rest of the classes that they're taking. Because who doesn't want to take a class and build a musical instrument in a semester? It's just really fun, whether or not you have a music background. And these courses have evolved over time. They're taught by faculty members in these different schools at Tufts, and they're also taught by a lot of industry professionals. So, my entry point to Tufts was while I was still working full time as an acoustics consultant. And able to bring in the projects that I was working on and experience in the field to talk about that with students. And there's a recording engineer who teaches courses, so it's a nice combination and kind of bridge between the kind of academic world and industry as well. And starting for the first time last year, and once again this summer, we have taken this material and the kind of structure of music engineering and the content that we get into and projects and activities at the college level, and we have transferred that into a program for high school students. So this is a 2-week workshop that happens over the summer on Tufts campus that's open to high school students. The dates and a link with a bunch more information about the pre-college program are right on the screen. The applications for this are open now and due on May 1st. But this is basically the intro to music engineering class that we teach for university students, but pared down and tailored to a 2-week program for high school students. So this is a way for high schoolers to get a taste of what it is like to be on a college campus, to take classes with college professors, to hear from seminar speakers from industry, from several different companies, to use facilities. So we kind of, in this particular program, we use a lot of the music facilities. We spend time in the concert hall on campus, but we also spend time in the maker spaces. and other engineering facilities. So this, we're very excited to be offering this again this summer, and would certainly encourage you to share this information with any students who you think might be a good fit for this. There are no prerequisites. This is totally open to students with a music background, with a STEM background. They don't have to have both. And we're really looking forward to running it once again this year. We are doing a free event as well on campus on Saturday, April 4th. The registration for that is coming soon. It's not up yet, but that's going to be an afternoon on campus where we're going to do a bunch of these activities as kind of a taster and get a little exposure to what this kind of content is like that we also cover in the pre-college program in the summer, and then that we also cover and get into in a deeper level at Tufts in the music engineering program. So once again, that link is there, and encourage you to share it with any students who you think might benefit from that kind of experience. So I want to shift now to talking about how we can teach through demonstration and hands-on activities and building instruments to teach about the fundamentals of sound. This particular intersection, the design and fabrication of musical instruments, is one that we find particularly compelling to students at a range of different ages, because there's a low barrier to entry. You can explain the physics concepts in a relatively straightforward way, and once again, like who doesn't want to build a musical instrument? This is a nice way to get students excited about applying physics and engineering and math to something that they can actually build and then play as well. So I'm going to walk through kind of a demonstration that is the sort of introduction that I like to give, for the first 5 or 10 minutes or so, and then an activity that is designed as a framework that can be expanded and scaled up or down in a bunch of different directions, depending on whether you're working with music students, math students, a physics class, high schoolers, middle schoolers, all of those things. So I I'm gonna exit this screen share for a second so I can actually just talk directly to you, and show you the kind of demonstrations that I like to walk through, and then I'll come back to the slideshow. So, um, and I find that sound, I've taught a bunch of acoustics classes and music engineering, and it is still true that sound is very difficult to talk about. The English language actually, like relative to other languages, has a particularly small vocabulary for describing the way that something sounds. So people often will like if you ask somebody to describe the way that a room sounds or an instrument sounds, they'll first like look at you like you have a few heads, and then they might try to kind of relate to other senses. They often use colors or temperatures or other feelings to try to describe what it is that they're hearing. So because we know that it's hard to talk about and people don't have a great vocabulary for describing sound, it's especially important to use all kinds of different media to introduce these topics and to give context when you're bringing this into the classroom. So I'm going to show a couple of physical demonstrations, and then when I pop back into the slideshow, I'll show some animations that resonate really well with students who learn in a more visual way. And I like to kind of do as many of these different things as we can. So what I have and I'm about to play is this hard plastic straw. It's a wide straw. You can kind of see how large it is. This is the kind of reusable straw that you'd find in a Stanley cup or another water bottle. So it's hard, it's not very flexible. And I've also stuck some air dry clay or some Play-Doh, something like that, into one end of it. And when I blow over the top of this straw, we'll see what happens. Is that making some sound? Give me a thumbs up. Excellent. Okay. It's always interesting when you're doing things with sound over Zoom. So how is this actually making sound? I'm not like pushing air through the straw that's coming out the other end, right? It's actually closed on one end. Even if it were open, that's not exactly what's going on. So when I am blowing over the top of this straw, I'm getting the air particles that are around my mouth and at the top of the straw to start vibrating back and forth. And as those air particles vibrate back and forth, they start bumping into their neighbors and they start moving back and forth. And those air particles bump into their neighbors. And you get this chain reaction that moves down the length of the straw. And that's wave motion essentially. And there are a bunch of great YouTube videos for how to create like a wave machine to demonstrate wave motion, which I recommend doing in the classroom. A slinky is another great way to show wave motion, and also a great way to distract kids and guarantee that they're going to, watch the slinky and definitely not listen to what you're saying. But as what's happening inside this tube, I can explain with a slinky, and so I like to do as many of these things as I can. Um, Now, because I have stuck some air dry clay at the end of this straw, as those air particles are vibrating back and forth and bumping into their neighbors, and that chain reaction or that wave motion is moving down the length of the pipe, once it gets to the end, it doesn't have anywhere to go. And so that wave motion reflects and comes back up the length of the pipe. And as long as I keep blowing into the pipe, that keeps happening over and over and over again. So I'm starting this vibration with my breath, and that's creating wave motion that's traveling down. I'm doing that over and over again, and I'm also getting wave motion that's traveling up because it's being reflected at the bottom of the tube. And when those things add together, we get what's called a standing wave, or resonance, which is why we hear a pretty clear sound that comes out of this straw. It only happens at a particular note, which we call a fundamental frequency, which is based just on the length of this tube, and the fact that it's closed on one end. And so, you could pull out a slinky to show this kind of demonstration. I mean, you can get a slinky to resonate at a particular frequency pretty easily, and at actually integer multiples of that frequency as well. If I wiggle it fast, I can get it into maybe a second harmonic. Usually when I do this in the classroom, I like to have students help me. But the reason that it's called a standing wave is because you can see particular spots where it looks like the slinky is not moving at all. So like right below my chin, the slinky is not really moving up or down. It's basically staying still. Whereas at my hand and around my shoulder, it's moving a lot. And what's happening is there are waves traveling in both directions on the slinky. They're adding together. And in some places, I'm getting what's called constructive interference, where those amplitudes are large and they're adding together. And at other places, they're exactly canceling each other out. And that resonance or standing wave behavior is what's happening on the inside of this tube and giving you a note that you hear. It's also great to, use a standalone tuner if you're in a music class and have tuners, or if you have a phone or another device. There are all sorts of free apps, like this one. This is a Tuner T1 app, but there are all sorts of different ones that you can use so that when I play a note, it will actually tell me exactly what note I'm playing and what its frequency is. So I'm going to try to do that once again. And I should be getting about an F5 because I've done this before with this particular straw, which is about at a frequency of 710 hertz. So 710 hertz or frequency is the number of complete cycles of that wave motion, if you think back to the slinky, that you're getting per unit time or per second. And if I were to take some shears and cut this tube and then play it again. Hopefully now, if you can hear that okay, you can tell that that note went up significantly. I could look at my tuner note and the tuner app and see what note, what note came out of there and what the fundamental frequency is. But the basic relationship is if we have a tube, we close it on one end, we can set up this standing wave behavior on the inside of the tube and get a really clear resonant note. And it's directly related to the length of the tube. So if I cut it, I make the tube shorter, I make my standing wave shorter, I'm going to drive my frequency up. And so a panpipe is an instrument. It's one of the oldest musical instruments in the world. Cultures all over the world have come up with instruments like this. The name panpipe comes from ancient Greece, named after the Greek god Pan, but there are similar instruments in many other cultures too, in ancient Mesopotamia, in the Zhou dynasty in China, in Andean civilizations in South America. And it's the basics are we have a panpipe or a pan flute, same thing, has a bunch of pipes that are all at different lengths. And as I blow over each individual pipe, I get a different note and I can play some music that hopefully sounds good. These pipes are typically closed on one end. They've been made out of all sorts of different materials in history. I'm going to show you some materials that I like to use for this activity in class. Um, but but this is a great kind of entry point to musical instrument design because the physics are really quite straightforward. All wind instruments, brass and wind and woodwind instruments operate on the same basic principles. They just have more advanced ways of changing the effective length of the pipe, and so changing the standing wave and changing the note that you hear. So for this instrument, I actually have to blow over a different tube to get a different note. Um, if I were playing a flute or a clarinet or an oboe, I would be covering and uncovering holes, which is effectively changing the length of my resonating air column. If I play a trombone, I'm sliding something and changing the length of the tubing, or pressing down valves on a horn or a trumpet, that's changing the length too. It's all working on that same basic principle. Um, all right, so let's jump back in. And I will show you a couple of animations that might be useful for some of your students, and then talk a little bit more about this activity. So there's a great collection of animations that I love to use in classes of all ages, all put together by a professor at Penn State. His name is Dan Russell. His website is here. But wave motion and sound in general, because it's difficult for people to talk about and they might not have background or context to draw from. I like to use the Slinky. I like to play instruments and record it and show what that looks like. I like to use animations like this and try to come at it from as many angles as I can. So sound is this vibration, this chain reaction, those air particles moving back and forth, bumping into their neighbors, and then creating this wave motion. And a panpipe works um, through this relationship between the length of the pipe and the note that I'm getting, or the fundamental frequency. Now, if you're working with younger students, or depending on what sort of objectives you're trying to get out of the activity, you may, just exploring that relationship between length and frequency without any equations is a great way to approach this activity. You certainly don't need to do it that way. If you want students to predict how long they need to make a pipe in order to achieve a certain note, you could do that too. It's just a sort of different flavor of the activity depending on the students that you're working with, and what backgrounds they have and how they're going to make the most out of the activity. So the equation is here: 4 times the length of the tube is equal to the speed of sound in air, which is about 1,000 feet per second, or about a little over 13,000 inches per second, divided by the frequency, that fundamental frequency. But if you want to do it with no equation and just cutting tubes and using the tuner app, that's great too. Um, a few more animations if you are in a more advanced physics or math class, and you wanted to talk about, on the engineering side, to talk about harmonics, and the fact that actually this tube is not just resonating at one frequency, but it's also resonating at integer multiples of that frequency, which are called harmonics. That's a great potential extension or expansion to go into. You could compare instruments made out of different materials and look at how their harmonic structure is similar to or different from each other. Audacity is a great free audio editing software, and just using the microphone built into your computer or your phone is a great way to capture that audio and be able to look at that data. If you're on the music side, I mean, the analog here is talking about timbre. So timbre is the multi-dimensional characteristic that allows us to distinguish between instruments that are playing the same note as each other, but that sound different from each other. And the reason that that quality of sound or character of sound is different is because their harmonic structure is different, because the time envelope is different. And this is an area that the aspect of timbre is something that you could explore more from a music perspective. as well as like what the musician can do to change the timbre. How can they alter the envelope depending on how they use their embouchure, or does the material impact the harmonic structure and the timbre of the note? Those are a couple of directions that this could go in. And this panpipe that I like using for this activity, or pan flute, is just a very basic instrument that has been around for many, many, many years. And it's just a collection of multiple tubes at different lengths. Okay. So the base activity of this, the challenge or the design prompt that I like to give to students, is that their goal is to build an instrument that plays at least 3 different notes. There are a lot of choices that they have to make in the process, a lot of variables that they have to deal with, like choosing from different materials, figuring out, exploring this relationship, the kind of fundamental relationship of the length of the tube to the note that you hear, how it's going to be closed at the end, how you're going to assemble it so that it actually like holds together and you can hold it in your hands and play it like an instrument. And then once again, a lot of opportunities for expansion. A couple of other ideas from the music side would be to use this as a way to talk about tuning systems, different tuning systems and different scales. You could, talk about the relationship of notes in different musical scales, and then have students build these simple instruments that can play in those different scales. Um, I mentioned before, you could use this to explore timbre and the harmonic structure. If you record the sound and look at it in an audio software like Audacity, you can look at what's called a spectrogram view of the sound, which allows you to see the frequency content of that note that you're playing and look at things like harmonic structure. You could have your students turn this into a different, like a percussion instrument instead of a wind instrument, and explore how that changes the timbre, either qualitatively or by recording the sound and looking at how the spectrogram or other visual representations change. You could think about the ergonomics, the playability, how you're holding this thing together, and how to make it easier and more accessible to play. Those are just a few of the different directions that I can see this going in. We have a couple of materials that we've developed that we'll share, that we like to use for this kind of activity, meant to be kind of adapted depending on the students that you're working with. So the first of those is what we call a placemat. The intention is that you could print this out. There are 2 slides. So this is 1 page front and back, that you could print out and have on the table in front of each student. And this is not a list of instructions or a list of materials saying, go over to this table and get exactly these things and make these calculations and then cut your tubes like this and then put it together like this. It's not that at all. The challenge, or this prompt to design an instrument that plays at least 3 different notes, is right, front and center at the top. There are some photos to give some ideas of what different instruments might look like. There are some questions you'll see at the bottom of this. Get yourself to think like an engineer, to think about how you can make your panpipe more resonant, or think about how you can make it easier to play. From the musician side, maybe think about the timbre and how you can control that through your performance techniques, or how you can tune your instrument differently. So this is meant to be a framework to give students enough kind of context to start out in the activity, but to give them a lot of freedom and creativity to go in whatever direction they want to explore, kind of meeting one particular goal. So if we look at the back side of this, there are some more questions meant to prompt students. Things like getting them to test different materials. It's great to do this activity with a bunch of different materials, and I'll talk in a moment about some of the ones that I have found to work the best, but it's important to mix in a bunch of materials that really don't work well and that are hard to play or that are not very resonant, and have students figure that out themselves as part of that learning experience. So different materials, figuring out how they're going to control the tube length. Are they going to cut it? If they're going to cut it, what material are they working with, and how are they actually going to do that? For some materials, that's easy, and for others, not so much. If you are going to seal it at one end, what material are you going to use for that? And if you want to make it resonant and sound good, you have to seal it really effectively. Is the material that you use going to change over, or its material properties going to change over time? And how are you going to deal with that? And if you, so a lot of questions like this to help kind of guide students and get them to think about different variables, but not to tell them, what instrument to build. It's meant to be a creative prompt. In the design and build section of the placemat, there's a graphic there of piano keys that is meant to be useful if you're trying to get students to build an instrument, like to predict the notes first, and then build an instrument to achieve those particular set of notes. So if they're going to use this equation, 4 times the length of the tube is equal to the speed of sound divided by the frequency, then this gives them a reference point for which frequencies they might be shooting for, using the piano as an instrument that a lot of people are familiar with. The particular notes or octave of the piano that I chose that's on this screen represent tube lengths between about 3 and 6 inches, which are, like generally what you will end up working with if you're working with straws or other kind of similar tubes that are easy to find. So that's meant to be useful, there to be useful as a reference if they're doing it in a kind of predictive way, or can be ignored if you're doing it in a more exploratory way. And then there's a reference on the right side there to using something like a tuner or a tuning app on your phone or other device to be able to measure what note your instrument is playing, adjust it. You will probably have like if students predict what length the tube, what they think it needs to be based on the equation, and then they cut it, and then they find that actually it's like a little bit out of tune, and now I have to figure out how much of this Play-Doh I need to stick in one end, and how does that impact the tuning. There's an iteration process built in here that's great for students to go through. And I like to save time at the end of class to have students play their instruments. It's even better if they will play it with each other. This kind of activity in general can work well as an individual activity, or it works well in pairs too. Larger groups, it's sort of best scaled to working individually or in pairs from what I found. And it's great to have people play something at the end, even if it's, assuming that it's going to be something like Mary Had a Little Lamb or Hot Cross Buns or something like that. And you could even, write out some instructions on the board or to give people, some songs that they could choose from to figure out how to play on their instrument if you wanted to. So that's the student placemat. That's the student side of the activity. So, there are lots of materials for them to choose from, and then that main reference in front of them. And then the other material that we've put together is meant to be on the teacher's side of this, to give a little bit more of a kind of suggested timeline of how you might organize this content into a class period, including some time for demonstration and introduction at the beginning, taking pieces, whatever pieces from the introduction that I gave a little while ago make the most sense for your own class, expanding or contracting where it makes sense. And then most of the time in the middle for students to build their pan types, and then time at the end to play their instruments and share with each other, and then also discuss the whole process, what sort of challenges they ran into, what they might do differently next time, and give them time to kind of digest and reflect on that. So this is also the point where I want to share some of the tips that I've learned from, playing with virtually every straw that I can find on Amazon or elsewhere. And this information is to help you, not necessarily to help your students. I really recommend that you have a wide variety of both good and bad sounding materials so that they go through that learning process. But if you look at the bottom of the screen, the example panpipes, I have each of those here with me as well. And I just want to kind of walk through some tips that I have, some things that I have learned from playing around with a lot of these materials. So this particular panpipe is made from, lightweight plastic straws. It's fun that they're colorful. I just assembled this using masking tape. Since the straws are lightweight, this is really easy to cut with normal scissors, great for younger kids. You'll notice actually in all of these examples that there is kind of a sweet spot in the diameter of the pipe. So like 3/8 of an inch or a half an inch works well for being able to play something and make a sound reliably without being a wind player, and having a strong embouchure. If you make it either much narrower, like a regular straw, or much wider. It's either going to be like too big for your mouth on that side, or if it's too small, it's very difficult to like concentrate that vibration from your own breath to get a good standing wave setting up inside the pipe. So I like this kind of width, no matter what material you're using, but again, mix in anything you want. Um, this is the easiest one to make because the tubes can be cut with regular scissors. Um, for the closure on this particular one and a lot of them, it's easy to use something like Play-Doh or air dry clay. On this one, and actually at some point in the last 20 minutes, you'll notice that like the middle one has lost its little seal on the end. So these straws are really smooth. Which is good on the one hand because you need smoothness to help set up a reliable standing wave, but because it's smooth, and as you play it, you're moistening the inside of the instrument. And when the air dry clay dries, it contracts, it tends to fall out. So it's not a super reliable one it will work well like in the course of the activity, but its longevity is limited. Um, it's also because it's lightweight, it tends to have an airier sound to it. So if I play, let's see if this one will still play for me. So this still makes a pretty loud sound. Hopefully that's coming through. But compared to the harder plastic tube, also closed on the end with air dry clay, it has a different timbre. I tend to find that the lighter weight instruments are a bit airier, a little less clear of a sound. They're not as stiff, they're not as heavy. So there's some limitations, but this is like the fastest and easiest way to get an instrument that will play some sound relatively well. It will also these instruments will also resonate and still make sound if you don't close them at the bottom. And actually, you'll set up a different pattern of standing waves and a different harmonic structure. That's a great thing to explore. But it's difficult to get it to sound loud. So I like kind of starting out with this activity, or if you're doing it once, to just have them close it at the bottom to get something that they're proud of at the end. You can tune it. This particular one I tuned by cutting them to particular lengths. Um, a different example like this one, I actually have all the tubes cut to the same length and I just stuck different amounts of clay in the bottom. So that's a different approach that you can take depending on what students are into or what materials make sense for your classroom. Um, any of these hard plastic straw tubes, which work well in the sense that they sound better as a musical instrument, they have a more reliable, clearer timbre, and they last a bit longer. The challenge is that they're harder to cut. You can't usually use a typical scissors to cut these. So like a pair of gardening shears works well, but you could also pre-cut a bunch of those ahead of time to short lengths like this, a few inches, and then have students change the length by adding different amounts of clay to the bottom. So that's an idea. Um, let's see, I've played around with a lot of paper straws. These actually are really easy to close on the end. The Model Magic or some kind of air dry clay or Play-Doh works great because the paper has a little bit of texture to it. So even when it shrinks a little bit, it still maintains a good seal. Let's see. So this still plays pretty well. I made this several weeks ago and it's still hanging in there. I haven't had to re-clay the bottom at all. It has I would say it doesn't have as nice, as pleasing of a timbre as the plastic variety, and that's because there is some texture on the inside of these straws because they're paper, stiff paper instead of plastic. Um, and so that standing wave does not set up as reliably. It, encounters some absorption along the way. Um, the instrument that I had the most fun and also the most challenging creating, which may be totally awesome and appropriate for your class or not, was to build this instrument out of a traditional material, which is bamboo. You can buy 6-inch sections of bamboo in bulk for very inexpensively. So that part is easy. Bamboo is also, if you see everywhere that there's a horizontal line, like near the bottom of one of these pipes in my instrument, that's a node in the bamboo stock, and it's actually already closed there. So if you were, you might sort of be able to see that, but like you can't see through these tubes. It's already naturally closed at that point. So you don't, that part of it is removed from the activity. But it's interesting because I mean, you can't see into this, so you can't see exactly where it's tubed. So you have to do a bunch of like experimenting with what is the actual like effective length of the air column. It's not the total length of the tube. It's actually something smaller than that, but it's kind of hard to see, and it requires a lot of iteration to get it right. Um, the challenge, this also I think sounds the best. It has a really nice clear sound. I like it a lot. It's just hard to cut. So bamboo really wants to split, like split along this direction. I mean, you could use a hacksaw or something like that, and that would be fine. If you want something that's a little bit more classroom friendly, I found these small like pipe cutters that are meant for narrow copper pipe. They're adjustable, so I can, spin a wheel at the bottom here to get this to be the size of my bamboo stock, and I can close it down. And then basically what I'm doing, I'm holding it like really gently to try to avoid it from splitting. And then the blade is right here, a vertical, and then I spin around the bamboo to like very gently score it around its circumference. And then I keep tightening this pipe cutter until it cuts all the way off. That's the sort of most classroom friendly gentle way that I found to cut these things without them splitting. It's fun to work with natural materials. They're unpredictable. And depending on your audience, that may be great or not. And this particular instrument, I assembled using some hemp, which works well because that string has a lot of texture. But there's a lot of, room for creativity in how students figure out how they want to assemble it. Popsicle sticks in this kind of like lattice of rubber bands are one particular method that I've used on a bunch of instruments. That's nice because I can actually space the tubes a little bit farther apart from each other, so it's easier to play individual notes. Whereas when the tubes are really close to each other, it's hard to avoid like making sound out of multiple pipes at the same time. Depending on what you're going for out of your instrument, that may be desirable or not. So lots of different things that students can explore with different materials, exploring this fundamental, simple relationship between note and length, but learning something about acoustics and sound and music engineering in the process. So we started out with this question at the beginning, what does music engineering mean to us at Tufts? What might it mean in your classroom? And, how could you kind of bring these worlds together? And this has hopefully given you a little bit of a taste of how interdisciplinary this is, and how many different fields it can bring together, music and engineering, and also art and design and physics and psychology. There are lots of different areas, and that's part of what I think makes music engineering really fun and unique. There are not very many universities that have courses in music engineering. It's quite hard to find. And I think it really appeals to students from a whole range of backgrounds. Again, whether or not they have a STEM background, whether or not they have a music background, it's a nice way to see how they can come together. Um, on the screen now are a bunch of pictures of projects and activities that the high school students who were part of last year's pre-college program put together. So on the upper left, there's a student playing with a theremin that's an electronic instrument. And let's see, the next one over is a speaker that students built with paper and magnets and copper wire. There's a MIDI drum kit that students built with an Arduino and cardboard and lots of tape, and some PVC piping. We spent a lot of time in Disler Hall, which is the concert hall on campus, jamming on instruments and talking about the acoustical design of the room and how the room acts as an extension of the instruments and changes the way that it sounds. We played around with all different kinds of microphones and learned about recording and production. Every student built a guitar, and we're going to do that again this summer. So this is just a little taste of the kinds of activities that you could think about. They're all examples of how music and engineering can come together, and there are versions of all of these things that you could bring into your own classroom. Or you could send your students to Tufts to experience this as part of our pre-college program. So there's a link again at the bottom about that. And also we're doing this free event on April 4th, where students can come to campus for a half a day to experience some of these activities and a little taste of what that's like. And music engineering is all of these different departments. It's lots of different possible projects and activities, but most importantly, it's fun. It's a nice way to help connect disciplines that students might think of as living in different worlds and show them how they can understand them through new lenses and broaden their horizons when they think about what they might want to study or what they might want to do in a future career path. So that's all I have for you. I'd love to take some questions if there are any.
Yeah, thank you, Kelsey. That was fantastic. Yeah, we are not using the chat feature today, so if you're in Zoom and you head over to Q&A, you can ask any questions there. Yeah, maybe Kelsey, would you say a little bit about what are some things you notice that the high school students are kind of doing or learning when they're doing one of these projects? I think these projects are so interesting, right? Because when we think about engineering, right, I have a friend and she's like, it's all race cars, rockets, and robots, which are awesome and fun. But I'm always so excited when we think about other entry point, when we talk about broadening participation, we talk about other entry points, and music seems to be such an interesting one. So I wondered if you could, thinking back to your work with students, could talk a little bit about like what do you notice them doing as they're designing instruments that gets you to be really excited?
Yeah. One of the reactions that I see that is like the most fun for me to watch happen is how surprised students are that they can actually build these things. Like the thought that they could put together wire and a magnet and some paper and connect a thing to their phone that actually turns into a speaker and plays sound, like blows students' minds because, they're used to using their very, high-tech headphones, well, what they think of as high-tech headphones and speakers, and they think of them as like this black box that some kind of magic is happening on the inside. But a lot, these things actually operate relatively simple at their kind of base principles, and it's amazing to watch. To see them kind of grasp that for the first time. And musical instruments are like that too. Like musical instruments have a lot of mystery and intrigue to them. And I mean, to make a wonderful musical instrument, is not something that any student is going to get to in a like class activity, but it's very possible to make an instrument that makes sound, that you can control the notes that are being played, that you can control the timbre. And so they're kind of, I see a lot of these projects as feeling like they initially felt kind of out of reach, and that realization and shock that actually they can put these concepts together relatively in a relatively straightforward way is really exciting. I mean, when you get like when the student plugs their paper speaker into their phone for the first time, they just like no matter what their personality is, their entire face changes because they just can't believe that they were able to make that work. Also, there's a lot of troubleshooting in the process, so it's very exciting when it finally makes some sound.
Yeah, that's such a great point, right? It makes these invisible things visible, and all of a sudden it puts this tech into kids' hands that they didn't think they had access to. And you're like, oh, actually, you could do that, which is so cool and confidence building. We have a
Right.
question in the Q&A. Um, do you cut the length of the straws using the Frequency ID app, trial and error? Yeah, maybe go through that part.
Yeah, yeah, great question. And you could do it in either of those methods. So, if the activity for you and your students is more about exploring this relationship between frequency and length, then you don't have to bother with the equation. You can just, as you cut the straws, use your tuner app to figure out what note you're hitting, and then, if you need to make it a little bit higher, then you're going to cut it a little bit shorter, and If you cut it too short and it's too high, then you either change the note that you're trying to hit or you pick up a different straw and you try again. So you can do it in that sort of trial and error way just by cutting and using the app. Or if you want to do it in a predictive way, the relationship between the length and frequency is that 4 times the length of the tube is equal to the speed of sound divided by the frequency of the note that it's going to resonate at. So, if you can work with that equation to come up with what frequency you want, maybe pick a scale that you're working in, say I want to hit A4 or 440 hertz, then I can plug 440 into that equation to back out how many inches or, whatever unit of distance you're working with to cut the straw to that length. And then you'll probably still have to do a little bit of fine tuning.
Great. Yeah. I definitely, just to piggyback on that, Kelsey came and did this activity with folks who are, like super music geeks, right? And she had the different scales from like Western and non-Western music. And it was really cool to think about, right? Like even just the decision making that goes into instruments about like what kind of sounds they're going to play. And so that was a really neat thing to think about having a conversation with kids about. Beyond the science and engineering of it, but like, like who decides what music we make. Oh, we have some more coming in. Thanks, Jake. At our school, we had a donation of insulation board from HP Timber in Madison. It can be used as a thermal insulator, but I was curious about how to have my students conduct experiments on sound absorption. Oh, I bet Kelsey has ideas on this. There are many opportunities in our district and community to support some sound reduction in different spaces.
Yeah, that's great. I hope that it was a donation of a lot because usually you need a lot of sound absorption to make a difference, like a meaningful difference to the way that a room sounds. So what kind of experiments could you do? I mean, the first thing that I like to have students do with a material is to talk into the material and talk into different materials just like qualitatively start getting a sense of how that sounds different. Like, talk into a plaster wall and then put this panel in front of it and talk into it. And can you actually hear a difference? Does it sound like your voice is returning to you in the same way, or does it sound like some of it is being absorbed by that insulation board? Um, Lots of different like actual quantitative measurements that you could take if you uh, if you have a space that is very reverberant, has a lot of sound reflective surfaces in it. You can measure the reverberation time of that room, or the length of time that it takes for sound to decay until you can't hear it anymore, by doing something like popping a balloon and recording that balloon pop and the resulting decay of sound on a microphone. And if you say you had like a gym that's often very reverberant, or some other space that's really lively, has a lot of sound reflection in it, you could make that kind of measurement and then repeat it as you bring more of those sound absorptive panels into the space. And then as you're changing the amount of absorption and then seeing how your data changes from that balloon pop measurement, you could back out this relationship and do some tests on how effective those panels are. Um, just a couple of ideas. Also, like if you know the thickness and the sort of general material properties, there's a lot of information available on, measured sound absorption data. There are like lab tests that we do to measure these things, but that's an idea for how you might do it in the classroom. I mean, putting it around people making noise of some kind, like playing instruments and putting the panels around them and seeing if it makes a difference, is another qualitative way to get a sense of how they're working. And then the main idea is you need a lot to make a difference. So putting a few panels in a giant room that's really reflective, you probably won't hear a difference, or not enough of a difference. You usually need a lot of surface area to be able to hear it.
Excellent. Yeah, Jake said he has tons, 50 panels.
Awesome.
So, Jake, yeah, you saw at the end of our presentation, and Lynn will send out again our contacts. Slide if you do that experiment, slide it into our direct messaging. Tag us on social media. We'd love to hear if you did some cool audio experiments. All right, we have another question here. Is the Audacity app preferred, best phone app to use?
Yeah.
What are your
So,
thoughts?
yeah, the Audacity app is wonderful. So you can use that. Actually, you can use it right in a web browser. You could use it on a computer. It works. There are versions for all platforms. Audacity is free and it's been around for a long time. It's an extremely powerful free tool for audio recording, and being able to see things like a spectrogram or frequency analysis, to visualize what's going on with sound. So if you're working on a computer and you want to get into that level of detail, then Audacity is always what I recommend. I mean, there are so many other professional audio softwares out there, but they all cost a lot of money. So Audacity is what I use in every class that I teach. On my phone, I don't really have much of a preference between different apps. Any app that is some kind of musical instrument tuning app, or some kind of tuning app that will tell you what note you're playing or what frequency, is going to all operate the same. It's all based on the microphone in your phone, and it's all doing the same processing. So the Tuner T1 app, is free on multiple platforms. It works reasonably well. There are a bunch of ads in it because it's free, but I don't have any special feelings about it. But if you're working on a computer, then Audacity is a great way to go, and it's free.
Great. Maureen has a question. Hello, my students have expressed an interest in mixing music and creating beats. Do you have any suggestions on programs or websites for this kind of activity?
That's a great question. Yeah, and I'm actually experimenting with ideas on how to do that myself to bring that into our pre-college program, and recording and production classes too. I mean, again, I think that it depends what audio software you have access to. I mean, Audacity is another good starting place because it's free, but it doesn't have as, GarageBand. If you're working on a Mac platform, also has a lot of stuff built into it. That's a nice place to start. Um, I don't have any like particular websites off the top of my head to share. I like, even if the kind of lesson is more focused on recording and production, I think there's still a great opportunity to have students create the sound that they're then using in that music. So whether they're using their voice or an instrument that they already have in play, or maybe building a new instrument and then recording that in snippets to put together music, I think that's a nice way of pulling kind of many of these things together.
Great. Okay. I think we got all the Q&A. Yeah, do you have any thoughts of how this might look different in a music class versus like a STEM class? Yeah, I wonder if
Yeah,
you thought about that at all.
Yeah, I think, in a music class, I think it's a great. I mean, you mentioned when I did this activity with you and some of your colleagues last year that we talked about tuning systems and different scales. I think that's a great this kind of activity, building an instrument, is a great vehicle for talking about what notes you're trying to get your instrument to play and what music is written for those notes and those musical scales. That's a great kind of exploration on the music side, as well as thinking about how the musician can actually control the note, the pitch of the note, and the timbre of the note, by changing their embouchure, by changing the way that they've changing something about the design of the instrument, by exciting it in a different way, like turning it into a percussion instrument. I That's something that I tend to focus on with music students, is how the musician can impact the timbre, the quality of sound that's coming out of it. And then on the engineering side, what are the design choices that you're making that are influencing the sound as well? Um, and then, in a STEM class, I tend to, I mean, I like to introduce them to different tuning systems and scales too. I actually like to do all of it, but I like to focus more on this fundamental relationship between, the note that you're hearing and the length of the pipe, and what is happening like on the scale, on the level of air particles on the inside of the tube, and using things like slinkies or animations or whatever is going to help your students to start to understand how sound is actually being created.
Excellent. Well, we're almost out of time here, so just check one last minute to see if there's any other questions. But I'm not seeing it. I think it's so exciting. I will say the other day that some Tufts alum came back to talk to some of our students, right? And they had done some of the music engineering work, right? They had worked on designing a violin, and now they're over at Shark Ninja,
Hmm.
Trying to figure out how to make their products quieter, the air filters and the blender. So it's real. I think it's really interesting to think about this space and how many places it is and how exciting it is to for folks to be able to combine these different kinds of spaces together. And we know that in the pre-college space, this is just a great learning opportunity that taps into so many kids' interest. And it's so tangible, right? Because you have this great feedback. I think whenever we do engineering projects, right, we want that iteration. Um, and right, sound is like, oh, that does not sound like what I want. I have a reason to do the redesign. Oh, we
Right,
got
the
one
feedback
last.
loop is like built right in.
Yeah, exactly, right? Sometimes it's not clear. Why should I rewrite this? Why should I solve this equation again? I'm like, oh, but it doesn't sound. We have a question from Elizabeth. What quick ideas might you share for younger kids? So like PK to first, pre-K to first.
Yeah, I love that. I mean, I have a preschooler in my house who I've had to keep these instruments away from. I mean, this is absolutely something that you could do. I mean, I don't know. My own 4-year-old is not great at cutting yet, but the sort of basic skills required are cutting straws. So you could totally make these instruments out of paper straws or plastic straws. Again, I recommend the wider diameter so that it's easier for them to play. But my older son has picked up all of these instruments and immediately put his mouth all over them and played them. I mean, that it's so exciting for them to pick up something like this and then immediately make a sound on it. So, basic straws that they can cut with kids' scissors, tape or rubber bands that they can use to put them together, and then, Play-Doh or Model Magic for the ends of them. All of those things are, easy for kids of that age to use. And, they as a function of building the instrument, they'll be exploring this relationship and between length and sound. But no matter what, they'll get something that they can blow into, and it will make some kind of interesting sound, and that's exciting for kids at that age range.
Yeah, definitely a great one to do, with a grown up too, where you might be like, how should I build mine? How could you build yours? What could we do to make it sound really low? How do we get that? Great. Well,
Yeah.
thank you so much, Kelsey. Thank all of you for coming today. We appreciate it. And if you decide to do all this, Lynn put all our contact information in there. We love to hear about these projects out in the world. The way some people like pictures of babies and puppies. We love pictures of kids doing engineering. So if you make panpipes or I do any kind of cool music engineering activity, we would love to see it, whether you slide it into our email or you post about it and we can reshare it with the world. You all are doing great work with kids, and we love to share and celebrate what you're doing. Stay tuned. We have more of these webinars coming up, and Lynn will also share out the recording from this one if you wanted any of these ideas or links. But other than that, have an amazing day. Stay safe, stay warm if you're in the Northeast, and we will see you for our next webinar.
Thanks, everybody. Thanks very much for having me.